Over 4,000 missiles were fired at the SR-71 Blackbird during the Cold War. None ever hit. This was a reconnaissance jet that flew faster than a speeding bullet, higher than 80,000 feet, and when enemy radar locked on and launched missiles, the pilot's response was simple: accelerate. And no SR-71 was ever shot down by enemy fire. And by the end of this, you'll understand exactly why the engineering behind this aircraft made it untouchable. To understand why something like this was ever built, we need to take a nostalgic trip back in time to the early years of the Cold War. The United States needed detailed information about missile sites, bomber bases, nuclear tests, and troop movements inside countries that would never allow open inspection. At first, high-altitude subsonic spy planes like the U-2 tried to solve that problem by flying above older fighters and guns. For a while, that height advantage worked. Then, radar networks improved, guidance became more accurate, and new missiles started reaching those altitudes. In May 1960, a U-2 was shot down over the Soviet Union. The pilot survived, and the wreckage was displayed to the world. That single event exposed the limits of the old approach. If the United States wanted to keep watching its rivals, it needed a different kind of aircraft, one that wouldn't sit politely inside the engagement envelope and wait to be shot at. The design targets were straightforward to write on paper and brutal to reach in metal. It should fly higher than 80,000 feet and cruise above Mach 3. Stay on station long enough to cross entire regions in one run. Carry sensors sharp enough to read details on the ground from altitudes where pilots could see the curve of the planet. And do all of that while showing as little radar return as possible. That challenge landed on the desk of Lockheed's Skunk Works team in California. Under the leadership of Clarence Kelly Johnson, they didn't tweak an existing airframe. They treated the problem like a clean sheet. If the main threat came from heat, drag, and radar, then the whole aircraft had to be shaped around those enemies. First came the structure. Ordinary aluminum, the usual material for airliners and bombers, weakens and softens long before it reaches the temperatures found on an aircraft's skin at Mach 3. At the nose of the SR-71, surface temperatures pushed toward 300 degrees Celsius. Around the engines, they climbed even higher. To handle that heat, the team built most of the airframe from titanium alloys, a family of metals that kept their strength when things got hot. Titanium brought its own problems. It was expensive, hard to machine, and it reacted badly during welding if there was any trace of oxygen in the area. Tooling and factory processes had to be rebuilt around it. Even the Soviet Union controlled much of the world's titanium supply at the time, so Lockheed sourced it through intermediaries without revealing what they were building. Even so, the payoff was worth it. The Blackbird could heat up in flight without collapsing or warping out of control. Then there was the shape. Those long Chinese along the fuselage blended into the wings and helped reduce radar signature while providing extra lift at high speed. The black paint wasn't just for drama on posters. It contained special compounds that helped the skin radiate heat away from the structure. At altitude, where the air is thin and cool, that ability mattered more than the amount of sunlight the surface absorbed. The airframe expanded during flight. At cruise speed, the aircraft grew nearly 10 centimeters longer. Panel gaps opened up. Fuel leaked out on the runway before takeoff, pooling under the wings in dark puddles. Engineers accounted for this. They designed the fuel system to use the airframe itself as the tank. No separate bladders, no heavy liners. The fuel sat directly against the skin. Sealant covered every joint, but thermal cycling degraded it over time. Maintainers constantly reapplied sealant. Leaks never stopped completely. They just established an acceptable leak rate and moved on. Inside, the aircraft carried powerful cameras, side-looking radar, and electronic receivers. From more than 25 kilometers above the Earth, these systems could map missile fields, track ship groups, and capture images sharp enough to study vehicle types at distances that would once have needed a spy on the ground. Of course, a sleek shape and strong metal did nothing if the engines couldn't keep up. This is where the SR-71 turned from a fast jet into something closer to an airborne laboratory. The Pratt & Whitney J58 engines under its wings started life as very powerful turbojets. In normal fighters, air comes through the intake, slows down, compresses, mixes with fuel, burns, and exits at high speed. At over 3 times the speed of sound, that normal pattern stopped working well. The air at the intake hit the engine face with so much energy that it caused dangerous pressure spikes. To manage that, the Blackbird used long, pointed inlet cones at the front of each nacelle. These spikes moved backward as the aircraft went faster, setting up shock waves at just the right position inside the duct. Those shock waves slowed and compressed the air in a controlled way before it met the compressor blades. The inlet spike moved backward 41 millimeters for every 0.1 increase in Mach number past 1.6. This kept the shock wave positioned correctly. If the shock wave moved too far forward or back, the engine lost efficiency. Worse, if the system failed to manage back pressure, the shock wave could get expelled from the intake entirely. This caused an unstart, a sudden loss of thrust that made the aircraft yaw violently toward the dead engine. Pilots described it as getting hit by a freight train. The inlet system corrected most of the time automatically. When it didn't, pilots had seconds to stabilize before things got worse. Next, part of that compressed air was diverted around the core engine and sent through bypass ducts toward the afterburner. 6 bypass ducts ran from the compressor to the afterburner, allowing air to skip the combustion chamber entirely. By the time the SR-71 settled into top-speed cruise, roughly 80% of its thrust came from this controlled airflow and the afterburner section, acting like a ramjet, while the central turbojet handled the rest. The fuel system had to match that strange engine behavior. Standard jet fuels would have boiled or ignited too easily in the hot tanks and pipes of the Blackbird. Engineers used a special fuel known as JP7. It had a very high flash point and stayed stable in conditions that would cause other fuels to misbehave. You could drop a lit match into a bucket of JP7 and it would go out. It doubled as a coolant. Before reaching the engines, JP7 was routed through heat exchangers that absorbed warmth from the airframe, the hydraulic systems, and the electronics. Once heated, it went into the combustion process and released the stored energy as thrust. There was one catch. JP7 was so reluctant to ignite that the aircraft needed help every time the engines were started or the afterburners were lit. That help came from triethylborane, a chemical that burst into flame the moment it met air. Small measured shots of this substance acted like matches for the main fuel flow. Each aircraft carried only 16 shots of this chemical. Pilots managed them carefully. Running out meant the mission was over. All of this would be interesting on a test stand. It became very real when the SR-71 went into service. During the late 1960s and 1970s, Blackbirds flew routes over and near Vietnam, North Korea, the Middle East, and along the edges of the Soviet Union. They launched from bases like Kadena in Okinawa and Mildenhall in the United Kingdom, refueled in the air shortly after takeoff, and then climbed toward their working altitude. The aircraft didn't carry bombs or guns. Its weapon was knowledge. Cameras rolled, sensors listened, and ground crews later developed film that showed entire regions in crisp detail. Opposing forces knew these flights were happening. They tracked takeoff patterns, tried to predict routes, and loaded their missile batteries. When their radars picked up a Blackbird, they reacted the same way any air defense unit would. Lock on, launch, then watch and hope. Surface-to-air missiles rose toward the track, climbing hard and turning their guidance fins to chase the target. On board the SR-71, the crew saw warning lights and heard tones as the systems detected search beams and guidance signals. The response was almost boring in its simplicity. increase speed, gain height, and hold course unless safety requires a shift. At the altitudes and speeds the Blackbird used, time and physics both favored the aircraft. Missiles had finite fuel. They burned hard during the climb, then relied on momentum. Surface-to-air missile systems like the Soviet SA-2 had a maximum ceiling of around 60,000 feet. The SR-71 cruised at 85,000. By the time missiles reached the thin air near the service ceiling of the SR-71, many had spent most of their energy. The target was also still accelerating. Tracking systems struggled to keep up, and the missile would begin to lose height, falling behind a jet that refused to slow down. Interceptor aircraft faced the same problem. The MiG-25, the Soviet Union's fastest fighter, could reach Mach 3 for a few minutes before its engines overheated. The SR-71 cruised at Mach 3.2 for hours. MiG pilots would climb, chase, and watch the Blackbird pull away. Their missiles lacked the guidance to hit a target moving that fast at that altitude. Even when they launched, the Blackbird's electronic countermeasures, speed, and altitude made tracking nearly impossible. Looking at the numbers, the performance still feels unreal. The SR-71 set official records in the mid-1970s for speed and altitude that no other manned air-breathing jet has taken away. It flew coast to coast across the United States in 64 minutes. On one flight from New York to London, it covered the route in under 2 hours. Normal passenger aircraft took more than 3 times as long. The aircraft provided intelligence that satellites couldn't match. Early reconnaissance satellites had fixed orbits. Adversaries knew when they passed overhead and hid equipment accordingly. The SR-71 could fly on demand, photograph installations without warning, and return with high-resolution images within hours. Film canisters carried thousands of feet of film. Cameras captured details from 80,000 feet that analysts could examine under magnification. From a strategic point of view, speed, height, and sensor reach changed how leaders made decisions. Instead of relying only on spies, intercepted messages, or slow satellite passes, they could request fresh imagery of a region and receive it in a useful time frame. Military planners saw exactly where missile batteries had moved, how many aircraft sat on a ramp, or whether a bridge still stood after a strike. More than 32 aircraft were built. 12 were lost to accidents. None were lost to enemy fire. That record remained unmatched. Pilots and ground crews worked around mechanical failures, fuel leaks, unstarts, and the sheer complexity of keeping the aircraft mission ready. Each sortie required a small army of maintainers, specialized refueling aircraft, and careful planning. The aircraft also influenced design work in other fields. Its engine control systems pointed toward later mixed-flow intake designs. The way it combined lower radar returns with simple acute angles fed into early thinking about stealth in later programs. Materials science, thermal management, and high-speed flight testing all advanced because of problems solved during development. By the late 1980s, new satellites and unmanned machines started taking over the missions the Blackbird once handled. The cost of flying it kept rising as the aircraft grew older, and the work needed to keep it ready became harder each year. Because of this, the SR-71 left regular service in 1990, although NASA continued flying a few of them for research until 1999. Today, you can find these aircraft in museums, sitting proudly in quiet halls. Yet they still look like they could take off the moment someone adds fuel and hits the switch. Honestly, they look more ready than I do on a Monday morning. For pilots, engineers, and anyone who loves aviation, the SR-71 remains the gold standard of high-speed manned reconnaissance flight. It combined advanced materials, powerful engines, and smart mission tactics in a way that let it enter the most dangerous airspace on the planet and return safely every single time. When you hear that thousands of missiles were fired at it without ever hitting one, it almost sounds like a tall tale. But the record is real. The Blackbird did exactly what it was built to do: fly into hostile territory, gather critical information, and leave before anyone could stop it. And here's what truly sets it apart. The SR-71 wasn't retired because it failed or because someone finally managed to shoot it down. It was retired because it worked so well for so long that newer and cheaper systems could finally handle its missions. No enemy ever forced it out of the sky. That fact, more than its speed or altitude, shows just how incredible the engineers at Skunk Works were. If you enjoyed this breakdown, make sure you like the video, subscribe to the channel, and hit the notification bell so you never miss our next deep dive.